Hello everyone, today I am going to discuss about some fundamental of powder XRD. Powder XRD, the full name of powder XRD is the powder X-ray diffraction. It basically the measure the diffraction pattern of the nanoscale crystalline material. It's it can be used in phase identification, sample purity, crystalline size, and the morphology. It quantitatively determines the individual crystalline phases, the impurities as well. Sometimes we use in nowadays in the in situ monitoring of the crystallization process, strain analysis, decomposition mechanism, and thermal expansion coefficient measurements. This this is the scalar equations, which is a quantitative approach to describe the broadening of the peak at a particular diffraction angle. So it basically relate the crystalline domain size to the width of the peak at the half of its height, that is denoted by the beta. So it is that half maximum height which is related to the crystalline domain size. It is d is equal to k lambda by beta cos theta, where d is our crystalline domain size, theta is the diffraction angle, and that is the beta is the width of half maximal peak. So we have related that beta to the d as per that Sacker equations. The question arises in our mind that is crystalline domain size corresponding to the size of the particles? The answer is no, because crystalline domain size may be composed of a complex of polycrystalline samples, so it may not be to the corresponding to the size of the particle. If we are sampling a single crystal, then it may be the equal to the size of the particles. This is the elaborations of how size dependent on the peak broadening. Such we can see that when we move from 1 micrometer to the 15 nanometers, its peak is going to broad slightly, and after that nanometer sized by 50 to 10 nanometer, we can we can find the significant uh, peak broadening of the XRD patterns, and after that 10 nm, so we can even find that overlapped and significant broadening of the peak we can find here. So it is not that much effective to find out the XRD pattern of that nanoscale material size, because of that peak broadening and the overlapping of the peak. That is the effect of morphology or the orientation on the XRD peak. That our crystal may have different orientation and the morphology, which also impact the XRD peak. Basically it impact the intensity of the peak, and like as we example that non-spherical particles orient in the random directions. So according to that random direction, they have some preferred orientations, and that affect that intensity of that particular family of planes. The peak position, the width of the peak remains same. It doesn't matter the which orientation we have our crystals, their position, the width of the peak will be same as characterized by that particular crystals. So that is some reason that why the preferred orientation occurs in our samples. It may be due to the quality and the size of particle shapes, and how XRD sample is prepared or dried. As we can see that this is a spherical pattern, that this is oriented in 100 family of planes. So that's why we can easily get the intense peak of that family of planes, and the rest of the planes are less intense as compared to that 100. The same is happen the non-cube surface, where they oriented in the 022 or 000K family of planes. So these peaks are looking intense as compared to the other family of plane peaks. And this slide cover the XRD analysis of the mixture of nanomaterial sample, in which we have two different sized nanomaterials in some particular ratio. So it's these type of XRD patterns are a little bit complex. It is not easy to read, because some peaks that have equal contribution to the same at same theta, they may overlap, and we can't define that what particular mixture or what particle component is belong to that peak. So that these type of peaks are necessary to refine or profile fitting methods to use these peaks to elaborate is more. These are some application of the PXID where we can use that powder XID formations that we can use in a face identifications, in which we can compare the experimental XRD pattern with the reference pattern, and we can check that what type of phase our crystal have. It is challenging for nanostructural materials because of very broad and overlay peaks are there. The second application is sample purity. Sample purity is basically from impurities which have very background noises. So we can't find that XRD peaks of that noise, and asymmetric peaks may corresponding to the stacking faults and other defects. So these may uh, find out the sample purity, the how much pure our sample is. That the, the very less, if our XRD packet have very less noisy or the background noises, then we can say that this sample is more pure than any sample who have the more noisy background noise in their XRD peak. The third is the lattice constants. Lattice constant, this constants determination is valid only for the high crystalline bulk materials. We can determine up to the 3 to 4 decimal places of lattice constants value. For that, we need to that profile fitting and refinement is required, like retailer refinements to exactly and inaccurately determine the lattice constants. In concluded slides, we have covered during this slide that the PXRD, what is the characteristic tools of PXRD, the peak broadening concept by Sacred equations, different size nanomaterials produce the different crystalline domain size, and we study the effect of the orientations and the morphology. We also discuss some overlay peak that we get when we have mixtures of different size crystals. We have discussed different application of PXRD, and PXRD analysis of the nanoscale is still challenging. To we have to work it more. The profile fittings have some good options to read that nanostructural material broad peaks, XRD peaks. That's all. Thank you.